up to this point, we've been looking at kinematics in 1 dimension. Now we're going to go to 2, and this will actually generalize quite easily to 3 dimensions, but we'll mostly be looking at 2 dimensions, 2-dimensional motion for what we're doing to start with. And so the idea is that I'm going to draw another axis, but this time we need to really pay attention. This is now talking about X motion and Y motion. So imagine you're looking down for right now at motion that's happening on a surface, okay? So, or you're looking forward here, and you can see my finger moves from here up to here, right? And the path that it moves would be its path in space. So it moves along here, or maybe there's a bug that's crawling along that line, and we can describe that motion as well. And this is where our vectors come into play. So we're going to go back and use some of our vector information here. So if I take motion that goes from this point in space to this point in space, okay, so it moves in a north and an easterly direction and a north direction, for example, then I'm going to describe its motion by a vector, any point that it is in space. I'm going to say when it's right here, I can describe its motion with a displacement vector, how far it is from the origin. And this S will have 2 components, right? It'll have the X distance that it is and the Y distance. So it'll have an X in the I hat plus Y in the J hat. And we can go from, say, an S initial to, let's say this is our final spot. Okay, that's S final, right? And so we can describe these with an X initial and a Y initial and an X final and a Y final. And how fast it takes to move along that path, of course, will give you something about its velocity. So velocity is just the derivative of this, how fast we're moving along. And you can find your velocity, because it's a derivative, it turns out you can find the direction of it by looking at the tangent to the path. So that's the direction it's going, but notice it has to sort of change directions here. It's like this and then like this. Okay, a derivative is the tangent to your path. It's your derivative, right? That's your slope, but it's the slope that's tangent to the path. And this we will write as dx dt in the I hat direction plus dy dt in the j hat direction. In other words, this velocity that we have, this little orange vector right here, this velocity at that point, that instantaneous velocity, is going to be given by the x component of the velocity plus the y component of the velocity. So we're definitely describing this with vectors. We can say sort of how fast it's moving in the x direction and how fast it's making progress in the y direction to get its overall speed. Okay, so that's its velocity there. And in the same way, we can say our acceleration is equal to the derivative of the velocity with respect to time. And so this, if we have this expression, we would say this is dvx dt in the I hat plus dvy dt in the j hat direction, or the acceleration in the x direction plus acceleration in the y direction. And if we have a third dimension, because we do live in a 3-dimensional world, then we would throw a z in here. So this could be extended to include a z in the k hat direction, which would then have a plus dz dt in the k hat direction, or a velocity in the z direction k hat, similarly with our acceleration. Now, for practical purposes, for what we're doing in intro physics and physics 1, we won't need that third dimension for a little while. It will come later in the semester. So for now, you can just stick with your 2 dimensions. So this is 2 and 3 dimensions, the more general case. Okay, so when we look at this, these components that we're interested in, then if we come back and look at, sort of zoom in on this place, so let's zoom in right here. So we've got x and y, and I want to just look at the velocity vector. So that velocity vector right there, so that's v, and it points in that direction. Then we can do our component part, which is we can divide it up like this, right? It has x, vx, and vy. And so we can describe this v as having a magnitude, v having a magnitude and a direction given by theta, right? Or it can be given by components, right? Vx and Vy. And from what we did earlier with vectors, it's not too hard to sort of figure out how to go from one to the other. Remember, we practiced this before, so now we're actually going to use it when we start to look at motion in more than one dimension. And so if we're going to, you probably guessed, we're going to go to SOHCAHTOA, sines, cosines, and tangents, so back to our trig, and realize that if we want to find our x component and we're given our magnitude and our angle, then this is the adjacent, theta is adjacent in our right triangle. If I blow this up just a little bit more. So here's our v, that, and this is our vx, our theta. This is our right triangle, then we can say, hey, the cosine of theta is equal to Vx over our magnitude. So if I rewrite that, multiply both sides by this V, I've got Vx is equal to the magnitude of the velocity. That would be the speed times the cosine, and then you can make the same argument to get to sine. Okay, and that's how you get the components. So you do still need to be able to go back and forth, and just for completeness, if you've given the components and you need the total velocity, the magnitude, of course, is given from the Pythagorean theorem, Vx squared plus square root of Vx squared plus Vy squared. Okay, so this is our general expression. It's useful, but we're going to look very quickly at some specific examples so that you're not worried that you're going to have to take derivatives right now while you're still, if you're in Calculus 1, still learning how to take them.